I'm just gonna give the folks who haven't yet found a seat a chance. Move up to the front of the room if you like. Don't be a stranger. So I think we'll get underway. Hello, everyone. Welcome to this online meeting of the Toronto branch of the Canadian Aeronautics and Space Institute. My name is Jeff Longadoc, and I'm the Executive Director of CASI. I'm together with my two colleagues from CASI headquarters, who you probably won't have the pleasure of seeing, Todd Legault and April Duffy, who are helping to make this event happen online today. As far as we know at this point, all of the events CASI will hold this year, including branch meetings like this one and for our other branches, our two major conferences, Aero and Astro, as well as other one-off events, workshops. They'll all be held virtually. So if you'd like to be kept informed of the many programs we'll be offering this year, I strongly recommend you become a member in CASI if you aren't already, and make sure your membership is up to date, and that way we can be sure to stay in touch with you and keep you informed of all the things that we'll be doing that you may be interested to participate in. So that's the ask today. The Toronto branch of CASI has been active since the Institute began in 1954. Over the years, it has played an important role in presenting programs by leading experts in every facet of aeronautics and aviation, and today is no exception. Our speaker today will be introduced in just a moment by the Toronto branch chair, Chris Hayball. Chris has chaired the Toronto branch of CASI for many years. The members and guests of the branch have greatly benefited from her accomplished career in aerospace engineering at what is now de Havilland Aircraft of Canada, and her desire to share her passion for aviation with others. I'm just going to check. Yes. Today we're quite fortunate to have amongst those who have joined the meeting today, Dr. Harry Cole. Harry is currently the principal of Royal Military College in Kingston, and we're very honored to have him also as our president. Harry, there he is. For those of you who are in front of your computer and you can see the thumbnails of the videos. Harry, welcome to the meeting. It's great to have you aboard. Would you?
Good evening, everyone, and thank you very much for your kind invitation. I'm going to try to see if I can make more of these. This is my first, and I'm really looking forward to it. Cheers.
Oh, it's great. I'm glad you can make it today, Harry. I know how busy you've been, and actually, Götz Bramesfeld, who is our speaker today, also has been teaching in this virtual environment, and it is really difficult for everybody. I understand that. My son, who is doing his PhD at York, is finding that the experience of being a student in a virtual environment is just as difficult and perhaps even as alienating as teaching in the environment can be. Hopefully that'll all end soon. And in the meanwhile, I know we're all forbearing and just trying to stay safe and be prudent. So back to the meeting today after that digression. Chris, with sincere thanks for your sustained commitment to the Toronto branch of CASI, it's my pleasure to turn this meeting over to you. Thank you very much, and carry on.
Thanks, Jeff. Hello, everybody. Good afternoon, good evening. I'm not sure what the correct term is at this time of day. 5 o'clock's kind of in between, but the evenings are getting so light out now that it's, I think, still afternoon. Anyway, hello, greetings. Thank you all for joining us. This is the February meeting of the Toronto branch. We had a very successful January meeting, and great thanks to the behind the scenes folks at CASI headquarters, Todd and April, who do the magic behind the curtain to make all this happen for us. Thanks very much. Looking forward to a very interesting presentation tonight. Our guest speaker is Professor Götz Bramesfeld from Ryerson. Just an example of how CASI is meant to work. He and I met a couple years ago at the CASI Toronto branch annual dinner meeting and got chatting. And he suggested that we might like to hear about his passion for soaring. And I said, yes, please, absolutely. And it's taken until now to actually make it happen. I guess he wasn't expecting it to be a virtual meeting back then. He was expecting it to be a in-person meeting, but such as it is, here we are online, and very happy to have Götz with us tonight to tell us all about soaring. So a quick introduction here. Götz Bramesfeld is an associate professor in the Department of Aerospace Engineering at Ryerson University. His research focus is applied aerodynamics and aircraft design, in particular with respect to small UAVs. Besides his professional involvement in aviation, Götz is an avid glider pilot with over 1,000 hours in gliders and a member of the York Soaring Association. He's also a board member of the International Scientific and Technical Soaring Organization, excuse me. A very keen glider pilot and professional interest in gliding as well. And we're looking forward to hearing about his research. So a warm welcome to you, Götz, and the floor is yours. The screen is yours.
All right, thank you. Thank you very much, Chris. Let me just share screen. All right, I hope you see my screen now. Should show several gliders. Chris, do you see my screen?
Yes, everything looks perfect.
Okay, excellent. Thank you very much.
Yeah, looks good.
All right. Anyways, well, thank you very much for this nice introduction, and also thank you for the opportunity to talk here in front of everyone here at CASI. CASI is being our professional organization. I think it's a very important part, and I'm glad to be part of this. My talk today is called 100 Years of Modern Soaring. It should be called 110 years or even more of modern soaring. But before going to my talk, let me talk about, tell you a little bit about my background. As Chris mentioned, I'm an associate professor of aerospace engineering at Ryerson University. My research is focused on applied aerodynamics and flight performance, and in particular also aircraft and aircraft design and analysis. These are my foci. Over the last 15 years, I've been mostly doing work in the direction of small drones, rotary ones or fixed wing ones, and this comes kind of from my passion about sailplanes. You can see here in the picture, this is part of my research group. Some of my research group members were in front of the large wind tunnel that we have in downtown Ryerson, and we did quite a bit of work with rotary drones like quad rotors and so forth. But also on the right-hand side, that picture shows another project of ours. That's this solar airplane. It's about, just to give you an idea, it's a 6.3 meter span and roughly 15 kilograms of flight mass. And this aircraft is supposed to fly at some point for several days nonstop. Last November, we were able to fly for over 10 hours, I think around roughly 10 and a half hours, which is, I don't think, too shabby for November in Southern Ontario. We're pretty excited about this, but I don't want to talk too much about this aircraft at this point, although I'm happy to answer more questions about this. Just if you're curious to visit us, where that arrow points in the basement, that's where my lab is with my students. We are called the Ryerson Applied Aerodynamics Lab, Aerodynamics Laboratory of Flight, or RALF. We like to use names for our projects. It's not always easy to find the right names. But besides the research that I do, what I really like to do is go soaring. And as Chris mentioned, I've been soaring since high school. In university, I went to university in northern Germany, in Braunschweig. There I joined a student group that has a long history in designing, building, and flying sailplanes. Then for graduate work, I went on to Penn State, in Pennsylvania State University in Pennsylvania. Primarily because it's located right on the Allegheny Ridge, which is great for soaring. So I've always tried, soaring was always the center part of my personal life, but also my professional life. Last year, I was at the German Aerospace Center in Braunschweig doing a sabbatical when COVID hit, and it changed the entire nature of that sabbatical. Also, I had all these plans of going soaring, but this particular picture is the only soaring flight I was able to do last year, which was in July with a friend of mine. We flew into the Austrian Alps for several hours, which was very fascinating, and it was a lot of fun, although I would like to do a lot more than that. Anyways, my talk today, I'm going to talk about general about what is soaring, a little bit background, how soaring works. Then I'll give a historic background, and then I'll talk about development, newer developments, because after all, I'm coming there from the engineering side, and I want to share you with some of the stuff there. Okay. Nope, wrong direction. Okay, what is soaring? And this, I looked it up in a definition. Soaring is motorized flight using a sailplane and naturally occurring atmospheric phenomena called lift to gain altitude and stay aloft. And we'll go into this in particular lift, what kind of lift mechanisms are available. Just to give you an idea of what's possible with sailplanes nowadays is currently the record in the total distance record flown is nowadays slightly more than 3,000 kilometers. The longest straight flight is 2,200 kilometers and some change. And the highest altitude that was reached so far was 76,000 feet, so over 23 kilometers altitude. These distance flights were all done in South America, indicated here by this line along the Andes on the Argentinian side of the Andes. And these were all flights done where the glider was towed up to altitude, released, and then basically flew on. And just also give you a little bit more background. All these records nowadays have to be done within daylight times, which means if you think about this for the distance record where they flew 3,000 kilometers, they had about 15 hours of daylight at that time, depending on what end you were at in El Calafi or San Juan. But that meant an average speed of over close to 200 kilometers an hour. And I think this is not too shabby for not having an engine. Just to give you an idea, for the longest straight flight that was done in Argentina, that would be the equivalent as flying from Bari to Iqaluit. Again, I think it's kind of impressive what's possible without an engine there. They used to keep records of endurance flights, but I think back in the 1940s or so, it was put away because it just became an exercise of who can stay awake the longest, and there was a safety risk involved with that. So this gives a little bit of an idea of what's possible with motorless flight. And how is it done? Well, this graphic shows a little bit the equilibrium of forces. For example, a powered flight, we have a weight of an aircraft which has to be compensated by lift. And one of the penalty of lifts is usually that we get drag. And so with the power airplane and a steady lift flight, we try to compensate for the drag by producing thrust with our power plant, whatever way it is. In a glider, we don't have this thrust component. And so as a result, we try to balance our lift and drag with our weight force. So part of the weight force is being used to compensate for drag, which means that the glider constantly trades altitude in order to overcome its drag. And so the glider, at least with respect to its air mass, always flies on a descending flight path, sometimes steeper, sometimes less steep. Just to give you an idea, modern gliders now reach to lift to drag ratios, which is basically a measure of the glide path angle in the order of 60, which if you think of it in degrees, it's it's about approximately a 1 degree flight path angle. And if you want to judge how thick that is, how steep that is, stretch out your arm, put out your thumb, and look over the top and the bottom of your thumb, and that's about 2 degrees. So modern gliders have a flight path that's shallower than that, what you measure. Like I said, gliders are constantly descending within the air mass, which means in order to do the distances, you have to find air masses that rise faster than the glider descends. So it's the analogy of being on an escalator that goes up as you go down. If you don't go down the escalator fast enough, the escalator keeps spitting you out on top. So again, the glider descends within the air mass, and then we find air mass that descends, ascends faster than the glider descends. And so this way we can ultimately gain altitude that we can then use to fly, do whatever we want to do. And these mechanisms, so at this point, I want to talk a little bit about the mechanisms that exist there for lift, essentially, that allows us to stay aloft. One of the oldest ones used in soaring is ridge lift, which is essentially you have a ridge, a hill, a cliff or something, and the wind blows perpendicular to it and is being forced upwards, and the upwards component of the wind often, if the winds are strong enough, can be sufficient to sustain the glider, and so you can fly along the ridge without losing altitude. The other common way of using lift is thermals. Thermals are essentially, what happens is the sun shining on the ground heats up the ground heats up the air above the ground. And we can see this sometimes in the summer day on a parking lot, where the parking lot is heated up the air, and you can see the flimmering because of the changing density. And as the heated up air usually is less dense, and then with some other mechanisms, it becomes buoyant enough to start rising. And then we have a fairly large mass of air that starts rising, and that also takes some other air with it, sort of like a hot air balloon without a hull. And then as it climbs, the air goes up, it expands and cools down. And if it rises high enough, eventually the moisture in that air package will condensate and form out these beautiful little puffy clouds that we see on days that glider pilots like a lot. And now with the glider, you go into this rising air and rise up while you and use this mechanism to gain altitude. This is a picture from the ridge near State College, Pennsylvania. You can see the ridge top is right here. The winds come from the right to the left. Usually the best weather is after a cold front has moved through and you have strong northwesterly winds. And the glider moves along the ridge. And on good days, you can easily sustain flight along the ridge, going 100, 150 knots. So roughly over 200 kilometers an hour steady while staying at ridge level. And people do it pretty regularly, go down along that ridge. It goes all the way down to Tennessee. I've been down to Virginia and back several times. And it's very exhilarating because you are essentially, for that flight, you are at low altitude, close to the top of the ridge. It's very bumpy, but it's also very fast. This is a picture of a glider's thermaling, and you can see it's a bank because it's in a circling flight, and here you can see the cloud forming out, and so somewhere in here is the air mass that is rising and that the glider uses to climb to altitude. Another lifting mechanism is called wave lift, and it's a little bit more. Let me try to explain. If you have an obstacle and the wind blows over the obstacle, under certain atmospheric conditions, you can have secondary waves below after this original obstacle. And the analogy, you can sometimes see this in creeks. When the water runs down a creek and there's a rock in the creek, the water runs over the rock, and then downstream of the rock, you can see these ripples in the water. The same thing happens in the atmosphere, and if the atmospheric conditions are right, these ripples can reach to very high altitudes and form out these standing waves. And with the glider, you try to find this ascending branch here, and if the wave works well, you can get very strong lift, and it's a very smooth lift, which is also a lot of fun. Often when this happens, the humidity or the moisture in the air, that as it rises, condensates and forms out these clouds, which are called lenticular clouds because they look like lenses. And these clouds, when you can see them stationary over a location, but they're not truly stationary. They just form on the front and dissolve on the back again. And especially in regions like front regions of the Rocky Mountains, when the Chinook winds blow, you can see these clouds, and this is when um, you can use wave lift. I've done wave flights along the Appalachian mountain ranges. I've been at 8,000 feet, cruising at 100 knots, and it's amazing. A flock of geese came the other way using the same lift as I did. So they know what's good as well. This is a picture of typical wave clouds. Here you can see the lenticular clouds, and here the front. Again, these clouds seem to be stationary, but the truth of the matter is they are actually forming at the front and dissolving at the back. Sometimes you can see them over southern Ontario, mainly because there's some shear action happening. You can have shear conditions where you can get similar clouds forming. All right, so for me, the ultimate fun of soaring is to go cross country. And that is basically you can have a declared task or you can just fly out free as you want. And what you do is you find a thermal, you climb the altitude, you then use the altitude to cruise to the next thermal, and then you climb up again. And then you repeat this until you finish your task or not. Sometimes you can't finish it. But anyways, from an engineering point of view, it's a very challenging design aspect because the glider, in order, again, I mentioned that earlier on, we are limited to the daytime hours. Also because thermals usually tend to die off when the sun gets lower. But so from a designer point of view, you have to have a glider that climbs well, but also cruises well. So the climbing part happens often in the high lift region, the high lift coefficients, versus the cruising happens at low lift coefficients. And so there's a series of trade studies that the designers do, and this is where I personally find a lot of the fun is from an engineering point of view. This is done regular. There are some pictures from cross-country flights. This glider is thermaling. These are cruising between thermals. There's some ridge soaring. It's a compound picture, just to give you an idea about what it looks like. So this is when you're in the air, but you got to get into the air first, and there are several ways to get in the air. Here on the upper right, you can see a picture of the probably older methods of getting into the air. And what is you're on the side of a hill, and you have a glider to which you attach a big bungee cord, which a bunch of people pull out while other people hold it in the back. At some point, that bungee cord is taut, and the people in the back let go, and the glider starts rolling and lifting off. All the people in front fall down, of course, which can be quite fun too. And then the glider sort of gets catapulted out into the valley, and hopefully can connect with ridge lift or thermals, or otherwise will just land in the valley. Alternatively, many clubs in Europe use winch launching, where you have a big engine pulling on a cable, and it launches the glider like you would launch a kite almost. I learned flying on a winch. It's very cost effective, but it's also a very unusual flight attitude, and so it's something you have to get used to. More commonly in North America, we use aerotows, where you have a power plane that pulls a glider up that is connected with a rope. You got to understand that the forces on the rope are not super high, because it's primarily it's dictated by the drag of the glider, which, if you think of it, is similar to 1 or 2 buckets of water, so about 100, 200 newtons of force. Then the other way to get in the air is to have your own motor glider, a self-launcher. There are lots of gliders which have little engines that pop out of the back. They have a little propeller. You start it up, you roll, you get into the air, you climb the altitude. Once you're in altitude, you stop the engine, stop the propeller, and then fold everything back into the fuselage. This is a good way to get in the air if you don't have friends. Just as a joke. Anyways, these things are being used for the regular soaring competitions, and if you get a chance to attend a soaring competition, I urge you. It's a very exciting event. depending on the competition, you can have up to 150 airplanes. They're all sitting there on the runway waiting for the weather to come. They have a declared task where the pilots are being told, okay, you got to fly there, there, and there. And the goal there is to do that task as fast as possible. So the average cross-country speed is the goal that you want to optimize. And it's quite a picture to see 150 gliders being towed up in the air within an hour or less by a whole armada of tow planes. It's a real dance. And then seeing all these gliders together in a thermal, where you sometimes have the feeling you could walk across the thermal from glider to glider because they're so close together. And then in the evening, all the gliders come back, not evening or late afternoon, come back, drop their ballast. Most of them fly ballasts, and I can get into this later on why that is. They do low passes and land in. And in between, nowadays with new technologies, we can follow the competitions often using GPS trackers and the likes. And so it has become a lot more of a spectator sports than it used to be in the past. And cross-country flying, like I said, is a lot of fun in competitions and outside of competition, but sometimes even the best intention of cross-country flights don't work out, and then something happens which is very normal for gliders, which is you land out in a field if the weather doesn't cooperate or whatever reason, and the expression is aller aux vaches, to go by the cows. And when you land out in the field, again, it's very common occurrence. You find out who your friends are who come with the trailer and help you to take the glider apart. And you put it off. Sometimes you can see on the highway, you can see these long trailers. They don't hold alligators. It's actually just a glider, fuselage and wings next to each other. They disassemble a good glider. You can disassemble easily in 15 minutes. You can also assemble in 15 minutes if you have an experienced crew. And again, these outlandings, like I said, are nothing unusual. I probably have done about over 30 in my lifetime. And they're always very exciting, and you get to meet a lot of interesting folks and farmers and so on the fields. Okay, so this gives you a little bit of an overview about about soaring and what soaring is about. I want to go now a little bit into the historical background of soaring. I want to go all the way back to Sir George Cayley, who in 1853 built a glider that he pulled up with his coachman on the controls, and supposedly it got airborne and flew across town a little bit and took out a chimney or so, and then landed. And after landing, his coachman said, like, quit his job because he was hired to drive a coach and not to fly airplanes. But anyways, Sir Cayley is the one we can sort of credit with the idea of having an aircraft where we have a lifting wing separate from a control surfaces, separate from a propulsion system. And probably, and this has been true for most airplanes, including gliders nowadays. The first more gliding flights or hops were done by Otto Lilienthal in the late 1800s in Germany. Lilienthal studied bird flight and then took this knowledge in order to build these hang gliders essentially, and did close to 100 jumps down a little hill, lasting a few seconds. Ultimately, he also became victim of an accident. Weight control is not always sufficient, and he crashed and then passed away as a result of the injuries later on. But he did some of the foundations and did some of early engineering approaches of studying bird flight and also different wing sections in order to see their properties. The Wright brothers picked up on that, and in 1902 actually flew their first glider to test out their control systems. And they did this in Kitty Hawk. In 1903, they got distracted with the development of the tow plane. But then in 1911, they actually went back and said, like, you know, Orville, Wright said to Orville, this gliding thing was a lot of fun. Let's try this again. And they built a glider again. I mean, 1911, 8 years after they did the powered flight, and actually flew this glider for a whooping 9 minutes, which was then the duration record back then for gliders. And they held this duration record for quite a while, and not until after World War II is when the Vampire glider was able to break this record with a first 1.5 hour flight and then increasing times by using ridge soaring. I need to take a little step back history-wise. So the Vampire was a design designed by students of the university in Aachen in Germany. And there's a little bit of a background. Germany has a rich history in soaring, and this kind of goes back to the fact that Germany lost World War I. As part of the Versailles Treaty, Germany was not allowed to do flight. Now, they didn't really specify there was flight in general, but they said powered flight. And just like here in North America, you had flight enthusiasts doing barnstorming with similar things. In Germany, you had people who were really excited about flying, and so thought, well, we're not allowed to do powered flight, so let's just do motorless flight. And they got together, and early on, these student groups at different universities were very instrumental in doing some of the early designs. Now, this glider was the first one to fly more than half an hour. And I want to point out that this glider actually has all the elements of a modern glider. It has an enclosed fuselage with a cockpit that's almost closed. It has a separate empennage, horizontal and vertical tail, and it has a cantilevered wing, no bracing, no struts, no biplane. And in essence, modern gliders have all these elements. They might not have the landing gear. This is actually a medicine ball. But overall, they haven't changed that much nowadays. In the 1930s, the development advanced further. This is the Minimoa. With this glider, first thermal flights were done. It was the same time, which then enabled longer flights and longer distances flights and longer endurance flights. Then after World War II, soaring picked up again. This was another German design, the K6C, I believe. And this is about the pinnacle of a wooden aircraft glider design. This glider has an NACA 6 series laminar flow airfoil. It has an enclosed cockpit, and it's a really nicely handcrafted, but it's about as far as you can go by shaping wood surfaces. And was then, however, very soon eclipsed by the new advent of composites air gliders. This is the first composites glider, the Phoenix, which flew first in 1957. It was designed by the student group of the university in Stuttgart. One of the students was Epler. If you guys are familiar with Epler airfoils, Richard Epler, that's where he learned his experience with gliders. And the interesting thing, this glider was like I said, out of composites, but it used rather than epoxy resin that we use nowadays, it used polyester resin. And if you ever worked with polyester resin, and it gets sticky in the summertime when it gets too hot and gets softer. So this is why we got away from polyester resins. But anyways, using composites allows us to get better contours, smoother contours, which then allows to have laminar flow airfoils. And also, because of the stiffnesses, we can now build higher aspect ratio wings or more slender surfaces, so better stiffnesses per weight trade-offs. Composite glider really took off. This is the SB10, which was built by students in the Götz Bramesfeld student club I was a member of. This was for many years the largest glider or sailplane in the world with 29-meter span. It's a two-seater. And it's also the one thing which I want to point out, it has a center wing with two outboard panels, and the center wing panel is the first composite wing that was built, I think, in general. The outboard wings are fiberglass wings, and you can sort of see how the bending line has a little kink here. That's the transition from carbon fiber to fiberglass. Like I said, this was the first time carbon fiber was really used for wing structure, and then it pretty much became a standard part of sailplanes designs. And then it enabled new designs and new designs configuration. The 1970s were very much dictated by exploring variable geometries. This is the FS29, which is a design by the Aerospace Stuttgart, again, the student group in the university in Stuttgart. And it had a telescoping wing, which could change its span from 13 meters to 90 meters in flight. Once you would use the large span for thermaling, and then for cruising, you would retract the wing. The pilot had a little lever, could pump the wing out and in. It was a lot of work, but an interesting concept of what we would call nowadays a morphing wing. A similar concept is the SB-11, which used a Fowler flap, which then, when you're in flight, you could extend the flap, which would increase the wing camber line significantly, but also increase the wing size by 30%. And so for cruise, you would retract the flap, and then when you get into the thermal, you would extend it to be able to fly slower and tighter in the thermal. This glider made a little bit of history because 3 months after its first flight, it participated in the World Championship in Châteauroux, France, where it won the first place in its class, the FAA 15-meter class. There's also variable geometry, some Canadian connection, which is the Sigma project, which was originally built in Great Britain at Cranford. In 1971, it flew first time, and it had a Fowler flap similar to a head of Fowler flap to increase the wing size. But then it was a little bit disappointing, and then Dave Marston from the University of Alberta brought it to Alberta and modified it, and it had a first flight in 1980. It was a somewhat interesting airplane that, again, could vary its wing area. I think he used a Fowler flap. No, he slotted flap that he could extend for thermaling for high lift parts. After all these variable geometries, there are some other geometries. This is a flying wing configuration, which is the SB-13 by the Ackerfleet Braunschweig, which flew first in 1988. If you're just wondering, the aircraft moves to the left. That's the back part of the glider. It's not truly a flying wing design. It's a tailless design because it has vertical surfaces and it has a horizontal tail. And I had the pleasure to fly this glider a few times. This is actually one of the few pictures with me in a glider. I was doing some experiments. The stuff you see in the at the trailing edge of the wing is a wake rake to measure profile drag in flight. And I'm sorry, here we go again, to measure profile drag in flight. This glider is retired, and I can give you more stories about it if you want to later on. Then in 2001 was the first flight of ETA as an efficiency, which is, to my knowledge, still the largest glider with a 30-meter span. It was made possible by using prepregs composites for the spar caps. There were, I think, 6 of them were built. It was sort of a private consortium of people who wanted to have the largest glider. And it's quite the show to see it because the wings are still very flexible and they don't always bend as nicely as in this picture. More recently flew in 2019 Nixus, which is a design that was designed by Paulo Iscald, a Brazilian designer. And it has a 28-meter span or 92-foot span roughly. And it's been flying some records. Last year, it did some speed records over 1,000-kilometer triangles. And the specific or special thing about this glider is it has a fly-by-wire flap system so that it automatically adjusts the flaps in flight and the pilot doesn't have to worry about it. So this gives you a little bit of an overview over the history of gliders. I want to now go more into this technical part. In the technical part, first I want to give you a little overview about what's happening. So this graph was given to me by Martin Heide, who was employed by Schleicher, one of the aircraft manufacturers. And I think as an aircraft designer, I find this graph fascinating. It shows here on the vertical axis the maximum distance flown, and on the horizontal axis the year. And you can see this is Lilienthal's flights here. Here is the Wright brothers, and then with the Vampire and so on, the distances grow and grow, and we're getting all the way to 3,000 kilometers nowadays where we are. And you can see these jumps, they are always associated with some sort of a development. Like the ridge soaring allowed us to get further by flying along ridges. Here, people got accidentally or purposely into thunderstorms. People don't do this anymore because it's not a wise thing to do always. But I like this jump here, mid-1930s, which has to do with the development of the Vario Meters. So the Vario Meter is an instrument we glider pilots use a lot. It's like a rate of climb indicator in a power plane, but not quite the same. So with a glider, you can gain altitude by pulling back and reducing and pulling back on your stick and soaring up in altitude. So you do climb, but you also lose airspeed, and so you don't truly gain energy. Yeah, you're just trading kinetic energy for altitude, for potential energy. And so the Vario Meter actually accounts for the changes in energy level of the glider, and so that made it much more possible for thermaling, and that had a huge impact on a relatively huge impact on the longest distances flown. Then you can see a new jump in with the advent of composites. Here, this is fiberglass becoming more common, and then this is directly related to carbon fiber. But the biggest jumps in the history of soaring are actually related not to aerodynamics, not to materials, but to, let's say, flight computers and GPS and weather modeling. So a lot of gliders, competition gliders or cross-country flights, use flight computers that help them make decisions on which thermals to fly, how far they have to go, what altitude they need. And this combined with GPS has become a very powerful tool for making in-flight decisions, whether to go a little bit to the left or to the right, or if we're ready to go home and get back to the field we want to get back to. The other thing which has had a huge impact are weather models. The weather models have become a lot more sophisticated, are much better to predict good soarable weather a few days ahead, and also to tell you that you rather go in a certain direction rather than another direction before you even take off, and so you can plan your route this way. And what I want to say is these 3,000-kilometer flights are still these long distances that we fly. We're flying with essentially gliders which are the same designs of the 1960s, 1970s. The aerodynamics have changed and improved, but not that dramatically. So a lot of the improvements on soaring have to do with like secondary effects like flight computers or weather modeling, which allows us to do better planning. Now, this has also had an impact on our design conditions, and I will go into this a little bit more. So the very new development in soaring that is having a definite big impact is electric flight. It enables motor gliders with much simpler propulsion systems because you don't have a combustion engine to worry on. There's just a little electric engine, which doesn't have a lot of drag. You can pop it out, you can pull it back. You have batteries in the wings, and they're easy to turn on and off. You don't have to worry about if it's too cold, they won't start and so forth. And even in the case if it doesn't work, the drag penalty is somewhat limited. So electric flight is definitely something here to stay in gliding for motor gliders, and we'll see more of that. Other advances are related to high altitude flight. This is the Perlin project. The objective is to fly to 100,000 feet. They've done the record up to 76,000 feet so far. And they're using, it's a whole team. It's sponsored by Airbus, but it's a whole team. And they want to get to 100,000 feet. And to do this, they want to use the polar vortex that gives us right now some cold weather in the northern hemisphere, also exists in the southern hemisphere. And here on the right-hand side, you can see an isobar diagram of South America with the tip of Antarctica. And you can see how the polar vortex reaches there into the South Atlantic, just northeast of the Falklands. And the idea is to use wave lift off the Andes to get up to altitude 75,000 feet, and then transition to the lift that's related to the polar vortex. And I have to be honest, I don't quite understand the meteorological events there, but this would provide lift all the way to 100,000 feet at least. And the nice thing is you don't have to worry about an engine that is starved of air because you are in a motorless airplane. And I think they will succeed very soon with this. Again, the time to do this is in the summertime, in the wintertime of the Southern Hemisphere. So stay tuned for that. I'm going to go on a little bit now to the design challenges. And I'm going to use this graph that Luc Boermans from the University of Delft in the Netherlands shared with me. And it shows the sink velocity versus flight speed of an ASW-27. That's a modern glider, relatively modern glider. And this is the predicted sink speed of the glider. So for example, at 200 kilometers an hour, the glider has a predicted 2.5 meters per second sinking. And at lower speeds, it's lower. And here we get to stall. And then our minimum sink is around here. And what Luc did is he computed out the drag penalty or the penalty due to the fuselage. So this would be this line, and then this line would be without the empennage. Obviously, we need a tail and a fuselage for flight, but if we could just fly with a wing, this would be the wing drag. So rather than 2.5 meters per second, we would have a little bit less than 1.5 meters per second sinking with just the wing. And the two things to take away from there is that at high speeds at cruise, where we enter thermal cruise, so between thermals, the majority of the drag of the aircraft is profile drag of the aircraft, versus at low speed, the majority of the drag thermaling, where we do here thermaling in this region, especially at high angles of attack on bank flight and high lift vector, high load factors, the majority of the drag is induced drag. And these are the two driving components from an aerodynamic point of view that we try to address. So let me go first into the aerodynamics. There's obviously a long tradition with laminar flow airfoils, natural laminar flow airfoils in soaring. But there's some ideas, and Luc Boermans works on this, to use boundary layer section, basically to manipulate the boundary layer in order to maintain laminar flow for a longer time and take the advantage of the low drag of the laminar airfoils. Not that new concept anymore. It's now already like 15 years old, but hasn't been really seen yet in practice. There's actually some wind tunnel tests going on about this. It's a slotted natural laminar flow airfoil that Dan Summers designed. And the idea is it's a slotted airfoil. It's like a slotted flap, but it works the way it works in cruise. The secondary element produce all of the lift that you need for maintaining for compensating for the weight, and the front element has fully laminar flow through favorable pressure gradients. And then when you want to fly slower, when you get in the region where profile drag is less of an important part, but induced drag, you load up the front section and you can get very high lift coefficients while at high, which allows you then to reduce the wing areas essentially and optimize your aircraft there. Like I said, this is a concept that's been explored also for commercial aircraft, or because this can also be used for like transonic airfoils. On the induced drag point of view, in the last now 30 years, the thing which has been the biggest change have been winglets and sailplanes. All modern air gliders nowadays have winglets. Also, new design methodologies and also production methods allow you to easier to have these very complex shapes of wings with polyhedrals, and there's a lot more happening. The other thing, which besides aerodynamics, which has changed, are advanced structures. This is the spar of the Nixus, the 28-meter span glider. It's out of a high modulus carbon fiber, which was built in this homemade autoclave. So it's a prepreg that's being laid up and then put into this autoclave to produce pressures higher than just 1 atmosphere. And here's a testing of this wing. So it's very flexible. So composites, even though these wings are still built here, mostly hand layup, enable us to have high aspect ratio wings or very slender parts. And this often causes issues with flexibilities. This is the Nixus set up for a ground vibration test because flutter is an issue. And this has been a challenge in gliders for a long time, flutter, and I have a little video here. Some might have seen this. Let's just turn the video off. And so let me explain to you what happens. So the glider is clamped out at a certain speed. This glider was ballasted just for this particular event. And the pilot would just excite the ailerons with a hitting the aileron. As a result, the wings, you can see the ailerons flapping up and down, and it's a adverse or an unfortunate interaction between the structural dynamics of the wing with the aerodynamics, which can keep this vibration going, possibly even to the point of failure of the wing. And it's pretty violent if you can see it. If you can look at this, you can see the tail even like wagging back and forth. Now the scary thing is that it's a very small speed band. By just reducing the speed by 5 kilometers an hour, the pilot gets out of it, and the flutter ends. So anyways, so flutter is definitely, or these aeroelastic effects are definitely a big thing in sailplane design, the practical ones. We've been like for a while been looking into if you can use aeroelastic tailoring, maybe to use the energy, extract the energy from gusts as you fly through. That's some work I have some graduate student working on, and I'm going to skip over this at this point. We're going to run a little bit out of time, but the idea is to use by tailoring the structure, the layup of the wing, we can have a certain bending, torsion, coupling that will allow us to reduce drag essentially of the aircraft. I mentioned that I was also at I was at DLR last year for a sabbatical, and DLR has actually a research glider. This is Discus 2C, which is equipped with a nose probe that has a 5-hole probe, and it has a data acquisition system and all kinds of data sensors to measure airspeed, altitude, and so forth. And it's a highly sophisticated airplane, and it's often used to measure the performance of other gliders by having them fly in the same air mass. And then knowing the performance of this glider, you can then back out the performance of this glider. And it's done very regularly with a very high precision, which is pretty amazing to watch to do it. But this glider is also equipped with an autopilot, and this autopilot is meant for the glider to fly high precision maneuvers. And the latest focus there is to explore turning flight performances. Again, because gliders spend a fair amount of flight time in turning flight, we want to understand the aerodynamics better. And the experiments are often used to compared with prediction models. And this is some work that I've done. So first, this is this discus model in an aerodynamic model. You see the wing here, you see the empennage, and then this is the wake during a 60-degree bank flight. And then this model allows me to figure out what are the drag components, what are the flow components, what is the lift distribution, what are our trim conditions, and so forth. And then we compare it with the flight test data. This is a comparison of the sink speed versus bank angle of this Discus 2C. These the red dots are experimental results, and then the blue ones are prediction models of the model. And this is where we're going to focus on. So this is a little idea about the research part, and I want to point out I'm part of the board of the International Scientific and Technical Soaring Association, which is OSTIF. It's a abbreviation of the French word for this, and and OSTIF has been around for several decades, since the 1950s, and is interested in anything, any technical meteorological aspects of soaring related to motorless flight. Every year, we usually have a Congress parallel to the World Gliding Championship. It was scheduled last year in Stendal, Germany, but was canceled because of COVID. And but it's again scheduled again for this year. There will be a remote option. I want to encourage you to, if you want to participate there with a paper, feel free to submit an abstract. We also have a journal, Technical Soaring. Check it out on the internet. It's open source. Also, the editor-in-chief, Kurt Zermes, sits in Montreal. I don't know if he joined us today. And if you have any questions, feel free to email me or contact me. Otherwise, I will point you in the right direction. But coming back to all the technical part, soaring has come a long way from the Wright brothers with their glider to modern high open class ships that are all composites, carbon fiber, and so forth. But at the end of the day, it's all about still about the fun of soaring. And here's a small little video that a friend of mine made at Gliderport, and shows you the progression of a flight. So the glider's hooked up for launch. This is a 2-seater. being controlled from the back right now. Up there, you can see the tow plane. So if you wonder, this is before I was in Toronto. I was working out of St. Louis. That's so it's in the Midwest of the United States. But it could be any glider port anywhere. They all are big fields. And so the glider is being pulled up by the tow plane. You can see it, that disappears a little bit under the nose at some point. It's a little bit of a flavor of what a local flight looks like. It's not too long, I hope. And the nice thing with the glider is also because you don't have a motor, it's quiet, fairly quiet. You hear the wind. And that's it. And the chatter of the people in the cockpit. Now the glider is flying a pattern to land. The field is here to the left off. You can't see it right now. And it's just a regular downwind followed by a base and then final with touchdown. And over in base. And turning final. You can see the field down here. Flaring and touchdown. All right, and if you want to check this out, okay, there is a view here in Southern Ontario. There are 4 very active glider clubs. I'm a member of Is Soaring, it's near Arthur, a little bit west of Orangeville. There's Toronto's Soaring Club, which is very active. Grey Lakes Gliding Club as well, very active, and SOSA Gliding, which is between Cambridge and Hamilton. Unfortunately, through COVID, most of these clubs are right now closed for the public, but nevertheless, once it's over, and it will be over, come on out to the fields. We're a friendly bunch. You can do guest rides. It's a great way to spend your time, waste your money and time. Anyways, yeah. With this, I'm at the end of my my talk, and I want to thank you for your attention. Thank you. Oh, if you want information, please feel free to email me or look at the website SAC, the Soaring Association of Canada.ca, for more information. Thank you. Chris, back to you.
Thank you so much, Götz. That was really interesting. An excellent refresher on aerodynamics and flight mechanics. Great to hear about your research, and especially great to share your passion for what's obviously a very enjoyable sport for you and for many people.
Right.
Thank you so much. I'm looking at the chat here. There's several questions. Perhaps you can entertain some answers for us. There's been a little conversation here going on in the chat about towing. Gary started off with a question. He said, I had the honor of driving a Ford pickup truck at the UK Lasham airfield in the late 1960s for auto tows. Is that ever used today? And then a couple of people have chimed in. Somebody said it's still used in Nova Scotia by the Air Cadets. Another comment, auto tow still done a little, not much anymore. Somebody else mentioned done at the top of the ridge in Pennsylvania.
Right, that's where I've seen it. Yeah.
And I don't know if you have any other comments you'd like to make about auto tows or other kinds of winch tows or launching mechanisms. I know you mentioned the different types in your.
So winch tows actually is interesting. It's becoming actually has morphed or developed quite a bit as well, and again with electric propulsion or electric motors. Unlike the so usually winches, older winches have combustion engines with an automatic transmission, and they have the problem that they have their maximum torque at 1 RPM. And in contrast to that, newer electric winches can have constant torque independent of the RPM, which is a real advantage when towing gliders. And so winches nowadays can get much higher altitudes. They also don't use steel cables anymore. They use I forgot, it's a composites, which is also used for bulletproof vests, not Kevlar, but anyways. But it's much lighter for the same strength, and so you can reach pretty amazing altitudes, and the cables hold longer. And auto tows, they're pretty exciting too. And I've never done one, but yes, I should have mentioned that too.
I have seen auto tows, not in operation, but obviously they were happening at a couple of airfields I visited in the UK. And there was a clapped out old car parked at the side of the field, and that was what they used for launching their gliders. Perhaps it's more of a UK method than the North American method. Interesting that you said that you're not using steel cables so much nowadays. I'm sure that's a safety thing. I can imagine that a steel cable, once it's been released, could be a quite violent thing as it comes back down.
Yes, you're absolutely right. But usually there's a little parachute between the release point of the glider and the steel cable, so the cable actually comes on a parachute, and so that dampens the rate at which it comes down tremendously. And so that's some issue. But the Spectra, the new cables they use are Spectra, out of Spectra. And the Spectrum material, first of all, it's much lighter than steel cables. And second of all, it's also much stronger on shear, so it doesn't experience as much abrasion when it's being pulled over the ground. When you pull out the cables, that's usually when they get used a lot, or where they lose a lot of their strength over time. And so Spectra cables have increased the safety a lot, and they also enable much higher altitudes because of their lighter weight.
Okay. Gary actually had another question right after the tow discussion here on the chat. Gary's asking, is variable geometry airfoil used? I recall that was a plan for the Cirrus glider many eons ago. I know that you mentioned variable wing planforms in your presentation, but what about airfoils?
Okay, let me see. I actually have, oh yeah, so this is, a friend of mine shared this with me. It's sort of a morphing structure where you can droop the nose for high lift parts, and he used like these mechanisms that are designed. So these are some developments which are in the making. There are some designs where they're still working with Fowler flaps. I know one of the student groups in Germany, they're building on a adjustable wing, basically an airfoil where you have a Fowler come out, or can you retract it? Yeah, so it's not dead, it continues, these thoughts, yeah. Obviously, like a mechanism like this, where you have a drooping nose, there's always these trade-offs. One of the trade-offs is very clearly weight, weight and complexity. The other trade-off is, like in this particular part, is gliders like to ballast their gliders in order to increase the wing loading, and the ballast using water. And the idea is then when you have a strong day where the thermals are very strong, the heavier glider might not climb as well, but you cruise at a much higher speed to get the same climb performance, glide performance. And so this is one of the essential parts. Can you take on water, and how would you put on water in this one? You don't want to put water in the back part of the wing for aeroelastic reasons, and so you would have to come up with a way to put water in here aside from the mechanism. So there's some technical issues or practical issues with this sometimes. You don't always think of it right away.
I'm not seeing your screen. I assume that you're looking at something on the screen. Are you able to share with us?
Yes, I am. Okay, let me do this all again, one more time. This. Thank you, Chris.
There we go. Now we have a picture. Thanks.
This is a drooping nose with a mechanism in there. And again, the idea is that for cruise, you have this shape, which is a low drag shape. And then for high lift part, for thermaling, you would droop the nose down and you would get higher CLs. And this way you can reduce the wing area for the same landing speed. Again, the challenge there is how would you put water in here? You don't want to put water in the back because, again, there's aeroelastic issues with this related to that. Okay, so I hope my explanation makes a lot more sense now. Thanks.
Just on the topic of morphing wings, I was interested in your example of the telescoping wing, and I think the span increased considerably, and you said the pilot had a lever to crank it out and crank it in. That must be quite a complicated mechanism.
All the pilots had really big left arms. Yeah, no, it's a pumping mechanism, and it works. The fact that no one else has done it so far is usually a good indication that it was not the best approach to it. It's definitely very fascinating, and to see that in flight, increasing its span from 13 to 19 meters. Yeah.
When you say pumping, is it pumping air to
No, it's a hydraulic. It's a hydraulic mechanism. Yeah.
Okay, back to the chat here. There's a couple of questions about a bit more technical questions from Paul. He says, did your wake rake drag match the wind tunnel data or match the CFD?
So yes, it did actually. So we compare. So one of the things is we didn't know, we had to estimate the lift coefficient, but we did measure the drags and estimate the lift coefficients based on the overall aircraft lift coefficient. And we'd taken the contour of the wing and digitized it, because the way you build wings is never the way you design it for. There's always inaccuracy that kind of gets into in the production way or manufacturing part. But we did compare it with compare the results with X-foil results back then, and it compared quite well. The main reason we used the wake rake was to do a study where to put turbulator tape. So on the lower surface, that flying wing has a reflex airfoil which has a laminar separation bubble on the lower surface, which at a speed of 120 kilometers an hour causes a whistling sound, because that laminar separation bubble keeps oscillating to the trailing edge back and forth, and it makes a really nasty whistling sound. Now, we knew that we can get rid of the laminar separation bubble by putting turbulate tape, so zigzag tape or knob tape on it to trip the flow to a turbulent boundary layer. And we knew that because the whistling was gone, we knew then that we were able to eliminate the laminar separation bubble. That, however, does not necessarily mean that the drag is actually less. Yeah, just getting rid of laminar separation bubble does not necessarily mean your profile drag overall goes back, because after all, you do increase your turbulent boundary layer length. And so the wake rake was mainly used to optimize the location and size of the turbulator tape. But we did also compare with computations, primarily Xfoil, and it agreed quite well.
So you were investigating a feature specific to the flying wing glider. Have you done other in-flight measurements with a more conventional glider design?
These wake rakes are being used on gliders in general, new gliders, again, primarily to figure out the optimal location of trip tape or turbulator tape, and also to optimize flap deflections for different flight speeds. As a matter of fact, this research glider that I showed earlier by DLR, the Discus 2C, they're flying around with a glove over the wing, and the glove has actually pressure tapes on it, and then so they can get the pressure distribution, and then they measure the profile drag at that section of the glove using a wake rake, similar to the one I showed in the picture earlier. And they're doing this actually for unsteady parts as you fly through gust or turbulence air, and then compare these results with CFD or other computational methods.
Okay, Paul has another question. He says, have you ever done oil flow viz? Probably difficult since angle of attack varies during the whole flight.
I've done that, we've done that, and we do this on a regular basis. It's a little bit more difficult in the wind tunnel in flight than in air. So we had a system where we could in flight spray oil onto the wing and then take a picture in flight. But you also can use a oil kerosene mixture with pigments, and then the kerosene evaporates after a while. So you gotta take off, fly at a constant speed, have it evaporate, and then they kind of capture the picture, and then you land, and then you can take pictures of it. It's very labor intensive, but you can do it. The other problem is, whereas in the wind tunnel, you usually have the model vertically, and gravity helps you to see a lot. In flight, the gravity is a little bit uneven. You can see that it runs as you get further back to the trailing edge of the wing. It runs easier because there's more incline with respect to gravity assisted, or same in the leading edge. So it takes a little bit of experience to understand what happens there. What's happening nowadays more is using infrared cameras mounted on top of the fuselage, and having a heating blanket or something like this, or just a black surface, to look at the different heat transfers through the laminar versus turbulent boundary layer in order to determine transition.
Okay, thanks. Paul's just posted a comment to your previous answer. He says, a great explanation, thanks. And I thought only my RC glider had laminar separation bubbles.
Oh, no.
Reynolds number of only 100,000.
Yes, that's the Reynolds numbers of the winglets usually. We're about chord Reynolds number about 1 million to 2 million.
Okay, here's another comment. This is from Harry, our CASI president, who's with us tonight. First of all, a compliment to you. Great presentation, well done.
Thank you.
And then he has a question. The cockpit of a glider looks a bit uncomfortable. Is this an issue? And if so, are there advances in human factors being pursued?
So I'm not the tallest person, so I find them comfortable, and I fit in every glider I want to fit into it. But yeah, you're right. It is human factors are an issue, and for multiple points of view. It's not unusual to fly several long duration flights. Like I've done flights over 12 hours, several. And so fatigue is definitely an issue. And that is part of the design constraints also, because it's part of handling qualities. The other thing is, in the last 20 years, there have been great advances with crash safety, because colliders do have accidents sometimes. And there have been great advances in making the cockpit safer, more survivable, and than previous designs. And so this is an ongoing project. But overall, in the glider, at least for me, most of the gliders are very comfortable. I feel very comfortable in them. You lay back you fill the seat, and I don't fill too much of it yet. And so there's still a lot of space, but it can get cramped with all the stuff like water and snacks and maps and so forth. Yeah.
Somebody's responded, Charles has responded and said, it's snug, but reclined for long duration comfort.
Right.
Just thinking about the reclining position, I guess that's partly to do with the shape of the cockpit. It's long and slender as opposed to tall, but it doesn't give you much room to flex your knees or wiggle around much on a long flight.
That's true, and it is your knees. My knees start hurting sometimes. I mean, you don't move your knees a lot because the pedals, rudder pedals, are usually just moved by your feet. And then because I'm always tense during flight because it's so exciting, then my knees at some point start hurting and I have to move them.
I have a question. Earlier in the presentation, you mentioned off-field landings, and you referred to being among the cows. I recall a colleague of mine, former colleague who was an avid glider pilot. He was flying at SOSA, and he didn't make it back to the airport, and he actually landed in the rhinoceros enclosure at the African lion safari.
Nice.
You said that you'd had 30 or so off-field landings in your gliding career. Had you had any exciting experiences of your own?
Oh, they're all exciting. I don't know. So one of the memorable ones is one of my last gliding out landings. I haven't landed out in a few years, but that was in Pennsylvania. I was flying out of Pennsylvania, and I landed out in Maryland, in Western Maryland. And there were these old folks that came up and to entertain me. You get to meet all these people, and one of the guys, he was actually an old Tuskegee Airman, which I thought was pretty neat experience to talk to him. Otherwise, people are generally very friendly. A friend of mine, we were flying in Hungary. He landed out at a nudist beach. So it was also a different experience. And yeah.
Obviously, you need help to get out of the field.
Yes, right.
And are the people that own the field, are they generally friendly, or do you have annoyed people who complain about you spoiling their crop or inconveniencing them somehow?
To be honest, most people are super friendly. They're extraordinarily friendly. They're very interested in what's happening there. Like farmers are usually the crop damage is very limited usually because the glider doesn't have a very big footprint. Most of the damage is done by carrying it out of the field. And so most people I've encountered were super friendly, super accommodating. I had one bad example where somebody threatened me with a shotgun. And I was in Pennsylvania, and I was only a couple miles away from the glider port. And to this gentleman's excuse, I have to say he had some bad experience where some glider pilot had landed and done some damage to his crop without getting back to him. And so I don't blame him for being upset about that. But for a large part, people are super friendly, feed you, you get to meet them. I don't want to land out, but it's not the worst experience. Yeah.
I'm glad you were able to do some gliding during your sabbatical in Germany. I guess you didn't do as much as you hoped to do. Did you have any particularly memorable experiences there, or perhaps in your not just in the past year, but in other time you've been gliding in Germany? Obviously, different landscape there than in North America.
So I have
the
to
Alps
say,
must be particularly spectacular.
So that was my first. This last summer was my first time in the Alps. I've flown in the Rocky Mountains, but the Alps was a very different experience, and it was very different to fly next to this wall of rocks, which went on for another 2,000 meters above me. And you look at the rocks, and you can't tell, are you 10 meters away from it or 100 meters away, because there's no telephone booth as a reference, and it's really hard to judge it. And so I was really happy that this friend of mine took me along, and he's very experienced. So one thing which I really like flying here in Southern Ontario is the fact that here it's 8,000 feet, and you do one circle. In one circle, you can see Lake Ontario, Lake Erie, Lake Huron and Georgian Bay. And I find that fascinating to see these giant bodies of waters just in real vicinity of my flight location.
They're not called the Great Lakes for nothing.
Yes. Yeah. So one of my most memorable glider flights, I have to say, was in northern Germany, and I was flying along cross country, and I ran across a family of storks, father stork, mother stork, and baby stork, and we started thermaling together. When you thermal, birds come with you or join you, and they know you, and they are friends. So we're trying to fly with them. And these storks joined me in the thermal, or I joined them, but we were in the same thermal and flying together. They climbed a little bit better than I did. And then we flew to the next thermal. My glide performance was a little bit better than their glide performance. And then again in the thermals, we connected. And I flew with him for about 45 minutes, which I think still to this day is like the most amazing experience in gliders that I had, I think.
That's pretty neat. Another question from Harry here on the chat. He says, how difficult is it to do applied research with gliders? Do you need special permissions to conduct flight testing? Do you need special qualifications?
So in Germany, there was a longer tradition, and sometimes it was just done. People just would do it. But there's also support, the DLR, the German Aerospace Center. They have a tradition in supporting glider research in these student groups that have different universities to support them. They see it in part as developing new engineering talent, and that's their investment. And it's a pretty high return for a fairly low amount of investment on their side. I don't know in Canada, but my experience with Transport Canada is actually that Transport Canada is actually fairly, in other experience I had with Transport Canada, they are very, very open for discussions, and these things are always open for discussions. I haven't done this with gliders. We're more concerned about drones, but again, I think it'd be possible. And if this is sort of my dream, I'd love to do some applied flight research with gliders and motor gliders here, maybe having a motor glider station at the downtown airport, the City Island Airport in Toronto that we can use and take students to. And therefore, if anybody wants to support us, you have my email.
Okay. Just curious myself, have you participated in any gliding achievement, like the different badges for distance or other targets?
Yeah, I've done targets, but I kind of forgot about them. I mean, I've done several 300 kilometers flights, 500 or 750. I've done even 1,000-kilometer flight. Now the 1,000 kilometers was sort of a cheating flight. It was what we call a yo-yo along the ridge, going up and down 3 times. But I've done triangles over 750 kilometers, and yeah. So and to this day, I think this cross-country flying is the most amazing thing. I'm always in awe when I'm, let's say, 200 kilometers away from home, and I'm there, and I realize I don't have an engine. It's without motor.
Yeah, it's pretty magic, isn't it?
Oh, totally, yeah.
I don't see any more questions on the chat here. I think I've answered everybody's. I think I've given you everybody's questions. Several people have put comments on the chat offering websites for different soaring associations that the rest of the audience might be interested in. So everybody can have a look at the chat for themselves and note the web address if you're interested. Oh, somebody's just popped up another one. Please compare motor glider and glider together. Sorry,
Okay.
just a second, my chat disappeared. Let me get it back again. Here we go.
Oh, I got it.
Please compare motor glider and glider together. Let us know about advantages and disadvantages.
Okay, so motor gliders used to be these clunky thing that were basically underpowered power planes. But with the newer gliders, like in the last 30 years with these pop-out engines and so forth, we're becoming more and more gliders that can launch themselves and get themselves at home. So the advantage of the motor glider is that you don't need a tow plane or winch or something like this to take off. Also, the other advantage is that before you land out in a field, you can pop out the engine, at least in theory, and then putter home on your motor power. But at the end of the day, rather to have to land out in a field and wait for somebody to pick you up. So that's the advantages. The disadvantage of the motor glider is it's not pure. I'm just kidding. But it's more complex. It takes a little bit more effort because you have to maintain an engine, and once you put an engine on an aircraft, the complexity increases not insignificantly. And oh yeah, the other disadvantage is you always carry the weight of the motor or the propulsion system with you. So in electric propulsion, it's not the motor, but it's the battery weight you got to carry with you.
And about how much do the batteries weigh for a motor glider?
I have to take a pass on this. I couldn't tell you right now. I'm sorry, but maybe somebody in the chat knows that. The Antares is one of the motor gliders you can buy. But I can't, I'm sorry, I don't know that.
Somebody's responded to the question in the chat here saying sustainer is much simpler and lighter and only to get you home, not to launch.
That's true. Charles is right there that a sustainer is basically a motor that doesn't have enough power to get you airborne, but once you're airborne, it has enough power to sustain flight and get you home.
Okay, I don't see any more questions in the chat, and that's pretty good timing. My clock says 6:26, so I think we've made very good use of our hour and a half here.
All right.
Just looking at the participant list during the course of the presentation, I think I saw a maximum of 50-something participants at one point. The number pops up and down. I've seen lots of familiar names on the participant list, very loyal CASI Toronto branch members who I've known for a long time. Other names that I recognize from the larger CASI community, but who aren't necessarily Toronto folks. Glad you could join us. And lots of other names that I've never seen before. So very glad that you could join us. I hope that you enjoyed your CASI experience tonight. And I hope that we'll see you with us again in the future for another CASI event. The Ottawa branch has been very active and they've been having virtual meetings as well. I've attended most of them. They're very interesting, and it's quite a different dynamic with the virtual meetings rather than the in-person meetings. I know we're all missing getting together in person, but there are some advantages that we can reach a much larger audience with the virtual meetings. So please do take advantage of what CASI has to offer in this new world that we're in right now. And there's lots of presentations, and I hope that you'll join us. I don't have anything else to say in terms of announcements or anything. As I said at the beginning, we're making plans for our March meeting, but they're not firm yet. But please watch your mailbox because the announcement will be out as soon as we can, and we hope that you'll join us for that. Once again, a big thank you, Götz, to you for your presentation tonight. Thank you for sharing your evening with us and sharing your research and of course, your passion for soaring with us. Very interesting and enjoyable presentation. You can hear the virtual applause from our audience here. I'm very glad that you could join us.
Thank you, Chris,
everybody else, thank you for being an attentive and interested audience, and hope that we'll see you again online soon. And of course, a big thank you to the CASI folks behind the curtain who have made our Zoom presentation pretty painless. I know that we often have technical glitches with these things, but I think tonight went very well. So thank you, Todd and April, and thank you, Jeff. I think Jeff has left the call, but thank you, Jeff, for starting us off. And I'll say good night.